In order to understand what it means for a point to be on a plane, we're going to backtrack from the equation of a plane. But first, we're going to define what it means for a vector to be normal to a plane. A vector is normal to a plane, which we'll from now on call said normal vector n, if a vector is orthogonal to the plane. Using that, the equation of a plane is the normal vector dot product whatever vector r, which is equal to the pointwise multiplication of the elements of both those vectors, is equal to a constant, and if so, that vector r is on the plane. Another way of seeing this is using the scalar product, the magnitude of the vector n multiplied by the magnitude of whatever vector on the plane r multiplied by the cosine of the angle between them is equal to a constant. What does that mean visually, though? What does that actually say? If we take the normal vector n, which is equal to the elements n1, n2, and 3, and scale it by some constant m, so that we go along the normal vector until we reach the plane, and take our vector r, which is just the elements x, y, z, and then create a triangle using these 2 points and creating the vector n minus r, we can note that necessarily this vector is on the plane, because this scaling to n took us to a point in a plane, and r by definition takes us to a point in a plane, so therefore, this vector is on the plane because we are creating it out of 2 points that are on the plane. Which means if it's on the plane and n is the normal vector to the plane, these 2 vectors are orthogonal. They form a right triangle, which means we can use trigonometry to define this total distance that we went along the normal vector to reach the plane, which would be exactly the magnitude of r times cosine of theta. So from there, if we multiply this by n's unit vector, which is just n divided by the magnitude of itself, we will reach the plane. This is what is called a projection of r onto n, the magnitude of r times cosine of theta times n's unit vector. Or in other words, how far we will go in the direction of n as we travel along r. You'll notice that if we choose to change r to another point on the plane, we get the same exact result. Which means, for a point to be on a plane, we could say that a point is on a plane if the projection of its point vector onto n is also on the plane. From there, in that case, if we just set this whole bunch of stuff equal to a constant, say for the vector itself, if we're given one point r and given an n, we can define what this constant is, and from there, if we can find all other possible r's if they meet this equation, by plugging and chugging and see if this crap equals the constant we were given. However, that's really messy, because you'll notice here when we changed the vector r, we also changed the angle theta, which means we'd have to calculate the angle every single time we want to determine whether or not the point we're given is on the plane. In order to simplify this, we multiply both sides by n squared, and then use the scalar product to change us back into the dot product, which is pointwise multiplication, which is way more easy to calculate. And then because c times the magnitude of n squared to the power of 2 is all a constant, we just wrap that into a new constant to make it look pretty. So a point r is on the plane if its dot product is equal to the projection of itself onto n, which multiplied by the magnitude of n squared. Okay. Now this gives us an understanding of what it means for a point to be on a plane geometrically, but it only works if we necessarily have the scalar product proven. So real quick, we're just going to go through the proof of the scalar product, but we're going to use a little trick to be able to simplify calculations so it doesn't end up being this huge mess of defining A as A1, A2, A3, and B as B1, B2, B3, and just crunching a ton of numbers. And the way we're going to do that is by taking advantage of the basis vectors. First, we're going to define the dot product literally as just the magnitude of A times the magnitude of B times the cosine of the angle between them. And then we will use that definition to prove the other side. First, we'll split A and B into their basis vectors, and then we're going to prove a couple axioms about this dot product by the definition we've just given, and the basis vectors. If we're using the basis vectors, this dot product is distributive. In other words, we can just take a basis vector and distribute it along 2 other basis vectors. We just prove that by plug and chugging each side and getting that they're both 1. We then prove that this definition of the dot product meets scalar multiplication for basis vectors. So if we take two basis vectors and we scale one by some constant, we can pull that constant out. Again, we just plug and chug each side. From there, we do the same process to prove that the dot product of two different basis vectors, I or j, is going to be 0 by this definition, and if it's the same one, it's going to be 1. We've already seen this one here, and to me it's very clear it's 0. The cosine becomes 90, and then cosine of 90 is 0, so I'm not going to go through the whole calculation of that. So from there, we take a dot product b, replace it with its basis vectors, and then because we've proven the distributive property, we distribute it out. Because we've proven that the dot product of different basis vectors is 0, if we get an I to a j or an I to a k, we just cancel them all out, so the only ones that matter are when the two subscripts are the same. And from there, because we've proven scalar multiplication, we pull these subscripts out, and then we just end up with exactly the definition on the right side. So because we've proven this definition using these axioms that we have proven, and we've defined the dot product on the left side to be the left side, we can just immediately say that the scalar product is proven. Okay. From there, the last thing that we need to talk about is what it means to increase the constant c in the plane equation. So previously we noted that c divided by the magnitude of the normal vector squared is exactly the distance from the origin we have to go along our normal vector to reach the plane. So if c is 0, that distance is 0. We don't have to go anywhere along the normal vector, which means that the point 0, 0, 0 is on the plane. If we increase c, we will then essentially be pushing our plane along the normal vector, and that the distance that we push it is going to be exactly c divided by the magnitude of n squared. There you go.